briefly. And for day, you were supposed to install a wallet. Were you able to all do that? Were you able to configure it for the test nets? Okay. Now, after you install it, were you able to fund it? Okay. So a few weeks ago when I wrote the lesson, I also had issues funding it, but this link right here works. So girlyfaucet.com. What you first need to do is sign up for an Alchemy account. I mean, don't worry about, like, it's just. No, you don't need, like, basically this is just a faucet. We're really not signing up for Alchemy to use Alchemy, and I'll go over what Alchemy is. But basically they just want to make sure that you don't create like a bot that just steals all the girly ETH. So that's why they ask you to sign up for an account, because then you have an email. You basically click on the verify my email. And then all you need to do is basically paste your wallet address in this field and say, send me. And do you all have your wallet with you? Like, is it on your machine that you have in front of you? So why don't you do that right now? Because that's can be a little tricky, and I want to make sure that you all have girly ETH, because later on you will need that in order to participate in the Ethernet challenges. So after you sign up for an Alchemy account, then you go to this link right here and then enter your address. And the address is your public wallet address.
Alchemy, and I find my public wallet address.
No, you have your public wallet address in your MetaMask. If you use MetaMask, right, the account. And then you just copy paste that in here, and then it'll fund it within seconds.
You need to actually type in your credit or your card. So this is probably
Yeah, and so here I have my girly testnet. I have my account, right? So I just copy that to the clipboard, and then go to this website. I have to first log in, which I don't have right here, but once you're logged in, you can paste your address right there and then click send me. Sorry?
I think there's a big cyanide button you can click on to escape that.
I did not get a monkey. All right, so which website are you going to? The Curly Faucet? And then you go where? Wallet address? I already did this, but let me.
Don't worry about it. The ETH will be sent to your wallet. You don't need to like interact with the energy stuff.
So if you go to your wallet, do you see 0.1 ETH? Perfect.
Yeah.
So you already have that? Mark, you're still working on it? Okay. So in the MetaMask, you need to go to advanced options. Oops. You go to, hang on, where is it? You can do show hide net test networks up here, I think. And you can go to settings, advanced, and then all the way, well, all the way in the middle, the show net test networks. Okay, so then after you funded your account, either send me an email, send me an email with your public address. Because later on, when you will do the Ethernet challenges, you will do those all on chain, and I can essentially see whether you completed it or not. Because everything on the blockchain is public. I don't think you can. Well, actually, hang on. There's a way. Expanded view.
You want us to paste our
Send me. Well, first of all, in Gurley Faucet, so you get your ETH, and then send it to my email. Yeah, just a public key, right?
send you public address
Yes,
to your email.
yes. So I just know whose account is whose.
But we need to create two separate accounts in each account and develop.
Oh, yeah, that's a good point.
So we send them.
Yeah. Did you hear Duke?
But each one has a different public key.
Yeah, so
That's right.
I think we need to send.
So if you look here, right, I have account 1, and then I have account 2. There, and so basically you just click on here, that copies the public address. You have both. And one should be, what did I say, Ethernet account, and the other one should be sure. Perfect. Thank you. And you have my email, right? I don't know. There you go. Seifert. Actually. Okay, Mark, I got yours, but I need both. And tell me which one is which. No, because basically what I will ask you to do is just transfer one, half of it to the other one. Wait, basically say you have account 1, you say send, and then you actually can say transfer between accounts, go to account 2, and then you transfer half. Good question. So to send digital assets, either the native or ERC20, you do not. You can just basically send it. If you want to change one digital asset to another digital asset, then you have to go to a swap. And so then you get, this interface, you click confirm, and then it will get mined. And in a few seconds, it should be. All right, let's go to the lesson. So we stopped here last week. So we basically covered symmetric, asymmetric, we covered hashing, we covered signatures, we covered Merkle trees. Yes, sir. A signature is generated by signing with your private key, and a signature is on a piece of data. So basically, think of just like a contract, right, or a piece of paper that you sign, right? So there's a piece of data that you sign, and it's really similar when you sign a piece of data with your private key. So it means that you verify the content of that snippet of data. And in blockchain, it is used to sign a transaction. Question? Okay, what is a Merkle tree and why do we have it? Let me repeat. So the leaves are the hashes of pieces of content, and then the parent of those two leaves is the hash of the two hashes in the leaves. And then it continues to go up. And so then at the top is the root hash. That is essentially a representation of all the data that has been used to build the tree. Basically, what I want to cover now is essentially how to build a blockchain. Because I think what we have covered so far are all the cryptographic primitives that are needed to build a blockchain. So what do we need? We need blocks that build on top of each other. We need the ability to exchange block information in a trustless way. We need the ability to verify the integrity of a block without the block needing to contain the entire state. We need someone to trust to create blocks, and we need the ability to sign and verify transactions. Once we have all those things, then conceptually we can build a blockchain. And so first we need blocks. Blocks that build on top of each other. And the way that is done is how? Hashing, and more specifically, this guy. Sorry? It's not a Merkle tree at this point in time. It's just a regular hash of the previous block, right? So we have XYZ, the block here, that's the hash of that block. And then that hash gets incorporated into the next block as the previous block hash.
As far as I know, like they for the block hash, like they will take all the block data or block data, and then they concatenate data, right? So and then they hash to get the block hash. Thank you.
That's a good question. Possible. I don't know exactly how it is generated, but that makes sense, right? Because basically what the block hash is, it's not just some random hash, it's the hash of the block content. So that makes perfect sense.
So I'm curious about the transaction 1 and 2 here. Are they like transaction hashes or they are the actual transactions, like the raw?
I think it's actually the root hash of the transaction Merkle tree. So again, it is, so this is actually incorrect the way it is listed here. The block will not contain all the hashes of the transaction hashes, because again, that's a huge list. And the reason for that is we want essentially the blockchain to be easy to distribute, right? We have several nodes on a blockchain, and so I want to exchange that with my peers. And so as a result, I don't want to transfer a ton of data. And so one way to do that, similar to how the Merkle tree optimizes storage of the smart contract, and kind of have a lot of the actual storage off-chain. Similarly, this happens here in blocks, where the block itself will contain the root hash of the transaction tree. And so then the block is super lightweight.
That mind, like, where do you think that the the actual transactions are stored since the nodes will need to like verify the root hash. Right?
That's a good question. I mean, I think there are also exchange from node to node, and they may be living on nodes as well, regular nodes, like full nodes. Think about a light node. It doesn't have to have all that state information. Hold on. Yeah. Make sure I'm still sharing. Just a second. I'm still sharing. Okay. Yeah, and that, Duke, that's actually a good point. So there are, in the Ethereum context, there are several types of nodes. There is an archive node, a full node, and a light node, and they have kind of a subset of the data. And a light node, I think, just has the blocks. A full node has the blocks with the state, and then an archive node has even more data. But I'm not 100% sure. But if you're looking, Duke, right now, enlighten us. And so what kind of the hash here generates is essentially integrity of the entire chain, right? Like, let's assume a block that was mined 4 years ago. If somebody tries to tamper with the data, then the hash changes and all subsequent hashes would not be valid, right? So it's basically integrity of the entire chain all the way to the genesis blocks of the first block that got generated. What I would like to ask you to do is open up your browser and go to etherscan.com. I think it's etherscan.com, and look up the block that I have here, 50,473,250. Would like to repeat that question, sorry.
So here you're hashing like A and B to get E. In this case, there's only one parent, right? Actual blocks that are being hashed.
Okay, this is the Merkle tree. It's different than the hashes here. So here it's just one parent. So it's just a straight up hash. There's no Merkle tree involved. The Merkle tree comes into place on how to represent the transactions. And the way that is stored is by the root hash of the transaction Merkle tree. So every transaction, let's assume this transaction gets hashed, and then hash, 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 and the root is being stored. Were you able to look up that block?
Yeah.
All right, what are the first 3 characters of the block hash? Is that right? You guys see that as well? Oops, hang on. Oh, I'm on Gurley. All right, so here we got the block. And if you click on see more, then you have the block hash, and then the parent hash is 60cc. Okay, going back here. Okay, so the next thing is that you need to have a network of nodes that are able to exchange information in a trustless way. And here's a specific protocol that is being used, but just think of it as a peer-to-peer protocol, right? Just like, you guys don't know Napster. What is it? BitTorrent, right? BitTorrent is still used. Yeah, okay. just like that, a peer-to-peer network. And so then I mean, we already touched a little bit on that. What information do these nodes exchange? So think about not just the blockchain structure, but also what the nodes work with. The state, yep, that's true. I'm sorry? Yes, transaction. So when I submit a transaction, I submit it to this node, right? And then maybe this node is the miner, right? That then will take my transaction. And so the transaction needs to move to that node. And basically that transaction is, as we discussed before, is part of the mempool. That's this temporary queue of unmined transactions. And so they need to be distributed in the network. State, state can be exchanged, but I think also state can be generated because, as you know, the blockchain is deterministic. And so theoretically, you could start from block 0 and execute every single transaction. You should come up with the same state. Now, nobody does that because it's too much history, but theoretically, that should be possible. What else needs to be exchanged?
Exchange LCNIS.
The what?
The LCNIS. Their nodes, and then they need to exchange the information of other peers as well. So because they are like interconnected, so
That's right.
Yeah, so they need to like do the exchange.
So they need to exchange node information, right? Essentially, the IP addresses of each of the node, because then I can start connecting to more nodes and get information better, and it increases reliability. And then, of course, the block. Okay, now you can do some Google searching and find out how many validators exist on the Ethereum network.
And some nodes are not miners that know that stuff. What is the software that they run on? Are they kind of like a server farm, or is it like just another kind of desktop here? Like what are their participation by the node? I guess I'm trying to like physically like centralize what this looks like.
So a node that doesn't mine really just needs to exchange information. And it needs to have a lot of storage in order to have the blockchain safe. And you can run that on the desktop, and you probably need a 2 terabyte SSD card. That's kind of the main thing on an Ethereum full node. Now, when you're a miner, again, we're talking about proof of work Ethereum. Then you need basically to solve the cryptographic puzzle. And on Bitcoin, you do that with specialized hardware. So it's essentially a custom circuit, hardware circuit that is designed to really just solve the cryptographic puzzle that Bitcoin uses. And on Ethereum, I believe it was ASIC resistant. So you couldn't design specialized hardware, and then it's just a GPU, a powerful GPU. And that's why the GPUs, by the way, I don't know whether you gamers, that's why the GPUs were so expensive, because all the crypto miners were kind of buying up the GPUs for mining. Now, the validator is different. You no longer solve a cryptographic puzzle, right? You're doing the proof of stake. You get randomly selected, as Oleg talked about, and then you basically propose a block. And if you do something maliciously, your stake gets slashed. And so that can be run on commodity hardware. You can run a validator. All you need is 32 ETH to stake, and that is currently about $45,000.
I guess, what's the incentive, like a node that just stores information or exchange information on the network? Is there no incentive, just like, I want to be part of the network?
That's a good question. I mean, I think it is, yeah, it's around kind of reliability. The other advantage of running a node is you now have access to blockchain information, right? If you can go to Etherscan, or you can go to some of the infrastructure providers and start interacting with like read the blockchain through those. But then you have an intermediate that sees exactly what activity you're doing, even if you just read the blockchain. Whereas if you have a node yourself, you pretty much stay anonymous. And so if you're like an MEV bot that tries to do arbitrage, you probably want to keep some of that secret, what you're looking at. Okay, how many validators?
Oh,
Yeah, 400,000 validators. That is insane. That is a lot. And I think for other for proof of work, it's harder to estimate. And also it doesn't really matter. It's more the hash rate that matters. Okay, so then we need efficiency. So we only store information you need in the block by utilizing hashes and Merkle trees. And that really allows for light clients to verify the blockchain integrity. And so it contains so a block contains the previous block hash. It contains the nonce. And the nonce is basically that random bit of information that the miner used to solve the cryptographic puzzle. It generates a timestamp. And then there is 3 root hashes. There's the state after root hash. So this is essentially a hash that represents the state of the blockchain. So think of all the memory that is associated with smart contracts. You have the transactions, again, the root hash of that, and then the transaction receipts. Okay, and then go back to your browser and tell me what the state root hash of the block is. That one, yes. And so, yep, exactly, Duke. And so this is, again, like if you think about the Merkle tree, that's G. And what is hashed is essentially all the state, the memory. Okay, and then you need miners. And we already talked about miners, so I'm not going to spend much time on that. But I would like you to look a little bit more at that block that got mined. So the same block, tell me who mined it. And let me just look at the date, because I think this was a proof of work block. So it happened before. Say again? Yeah, this guy, yeah. That's the miner. And so it was mined before we switched to proof of stake. Oh, so actually this one, right? This one was, yeah, this one was mined by this guy. And then how much did they get? How much ETH? Three. That's right. The 2 ETH, $3,000. They got $3,000 to mine that block. Okay, then let's continue to investigate a little bit. Tell me how often a block gets mined on Ethereum mainnet. Like what's the duration between each block? I'm sorry? That's also about right. So that's the Ethereum mainnet. What about Gurley? $50? 15? Okay. So very similar to then Ethereum mainnet. What are the three main, and so here it's really not mining pools on Ethereum mainnet, but rather the validator pools. And let me briefly talk about that. So Mark could have 45,000 extra cash. He buys 32 Ethereum and sets up his validator node at his house, right? And then, you know, every epoch, he gets some ETH as a reward. And now he has a computer that he has to buy, has to maintain. So it's a little bit of pain in the butt. There are these companies that essentially will do the staking for you. So you will send them a smaller amount of ETH, let's say 5 ETH, because you don't have 32 ETH. And then they will pull that all together. And then once there's 32 ETH, they will create a validator. And they will run it for you. And then basically they will take a cut of the rewards and send you the remaining rewards, right? So it's essentially staking as a service. And so question is, who are the biggest staking as a service providers on Ethereum mainnet? Sorry, Coinbase, Kraken. I think Coinbase, Lido, and then Kraken is a little smaller here. I had a chart up. Yeah, so we have Lido, which is the biggest. Unknown, these are likely individual validators. Coinbase, Kraken, yeah, so. So do you see a problem with that? Yeah. Now you have to think about that they have, you know, probably billions of dollars staked. And so if they behave maliciously, then they get slashed by the protocol. But the issue that arises if you have somebody like Coinbase, who is a publicly traded company, the US government could say, all your validators that you're running are not allowed to do these sort of transactions. And the US government, just a couple of months ago, put the Tornado Cash service on the OFAC sanctions list. Tornado Cash is essentially a mixer. It allows you to send transactions between accounts without seeing that link. right? Like when you send a transaction earlier from your account to the other account, you see that clearly on chain. And so think of, instead of doing that, you send it to this intermediary where a lot of people deposit funds, and then you can withdraw from that intermediary to a different account. And so that link gets broken. And that service is often used in attacks. And the US government didn't like it. And so they put it on the sanctions list, meaning if you use the Tornado Cash protocol today from within the US, you may get into legal trouble. And so what could happen is that they say, Coinbase, you're in the US, you're not allowed to mine any transactions that involve Tornado Cash. And that essentially would constitute, some first of all, government control and permission system and sanctions. In that particular instance, is you need a lot of liquidity in the protocol in order for that to work. There need to be a lot of people that deposit. If there's only, this class, then it's, even if the link is broken on chain, probabilistically, it's easy to figure out who sent what, right? Okay, and then you need essentially transactions that are signed with a private key of the users using asymmetric encryption. And we demonstrated that last Tuesday when I did a swap, right? I swapped token X for token Y. And the way I did that is I signed a transaction with my MetaMask that basically says, send the funds to this contract, invoke this function. And that transaction then is essentially signed and then submitted to the nodes. It gets distributed across the nodes as part of the mempool, and then some miner will pick it up. All right. So if we go back to the slide here, we have blocks that build on top of each other using hashing. We have the ability to exchange block information in a trustless way through this peer-to-peer network that, of course, is encrypted and use signatures. We have the ability to verify integrity of the block without the block needing to contain the entire state by using Merkle trees. We trust someone to create blocks in proof of work. That's through the cryptographic puzzle. And then we have end users that are able to sign and verify transactions and submit those on chain to get mined. So those are really all the building blocks that you need to build a blockchain. Not that complicated. Glad you didn't laugh, so. All right, so for assignment is build a blockchain. No, we won't do that. That's the 201 course. All right, well, let's take, let's be back here at 7:05. And we'll talk about Ethereum deep dive / scratch the surface.